So let's take a look. What kind of nice property can we find in an array of counters? Let us use a simple example so we can see that nice property easily. Yeah. Given a bit array. So this array is very special, bit array. The values for its elements only can take 0 or 1 bit value like this. Okay. 1, 0, 1, 0, 1. Very simple. Yeah. Now the question, how to count the number of zeros and the ones in this array? Simple, right? So write a program to do it. Also very simple. Yeah. But here, we try to find something interesting. All right. So here, the key to the solution. What's the key to the solution? Here, we want to use a counter to count. Okay. Use a counter, some special array of counters. We define an integer array, CARR, integer array, new integer value, right? 2. Array size is 2. Okay? So only 2 elements, CARR of 0 and CARR of 1. Okay? So simple, right? Yeah. But why it is useful? Yeah. So let's look at that. So here, the array size 2, why we use the array size 2 here? There is some reason. Because we only have 2 values for our array elements. Our array elements can only take 2 different values. Those 2 values correspond to 2 elements in the counter array. Yeah, so very natural. 1 element targeting 1 value. Okay, yeah. So that's why, yeah, there is some reason. Yeah. Here you can see array values and the counter indices. There is a 1-to-1 correspondence. Array value 0 corresponds to index 0. Array value 1 corresponds to index value 1. That straightforward relationship. Okay? Yeah. So with this observation, so you can see if we want to scan this array once and do the counting for different values, there is a very easy, simple way to do it. Yeah. So look at this for loop. Okay. I from 0 to the array length. All right. Look at the key line here. Key line here. In the array index part, we use the A value, A of I. This is the A value. Because A value can only take 0, 1. So we never, when we use this expression, we never get out of bound. Always in the bound. Because we declare this array size covering all the possible values. So always in bound. Okay? So always legal. Then we do the incremental operation. So here you can see each array element at the end, it will get a counting number for that particular value. Okay? So simple, so straightforward, so efficient. So this is really nice, brilliant expression. Okay? Yeah. So this thing, yeah. Remember here, we're using an array value as an index. This is the special thing. array value as an index. Yeah, that's the special step we take. Yeah. And this line gives us the idea, the sense, art of programming. Yeah, because this line is so smart. Okay? Although it's very simple, but extremely efficient. Yeah. All right. Next, we want to generalize the idea. Yeah. The bit array is still too special. We want to consider a more general array. Yeah. So this time, we take an integer array with values in this interval range from 0 to k. Yeah. Now we can use the similar idea. We want to count the number of elements that take each value. Yeah. So to do that, we just generalize the previous idea in a straightforward way. Straightforward extension. Yeah. Now, this time we take k plus 1 values, because from 0 to k. So each value, we use one counter to do the counting. Yeah. So we need k plus 1 elements. Right. Then we run a for loop and using the same way we used before. Yeah. So that's a perfect way to do the counting. Yeah. All right. Next question. Does the counting help the sorting? Yeah. We can get the counter numbers. Yeah. We can get the counting numbers. Now, because our goal is sorting, can we use those numbers to sort the array? So that's the question we need to answer in the remaining of the solution. So now we are doing analysis. So we have a long way to go to find a solution. All right. Counting for sorting. Yeah. We try to look at from some simple example. We always use simple example to inspire us thinking. Try to find some rule, some property, so we can generalize, and eventually we can solve the problem. Here. So let's consider a simple example like this. Still that bit array, right? Yeah. Simple, but it's enough. It is good enough to give us some idea. Yeah. All right. If we know that we have 4 zeros, yeah, because after one scan, we can get 4 zeros, 6 ones for 2 counters. How do we use those 2 values to get the array sorted? Yeah, so that's the question we want to answer. Okay. All right. So the answer, something look like this. Okay. Yeah. First 4 0, then next 6 ones. Next 6 elements, all ones. Yeah. So that's the sorting result, right? Very simple, based on the counting numbers. Yeah. All right, so now there is another question. Yeah, because we feel we need to consider a little more for the situation like this. Yeah. So let me ask another question. Can we simply pack 4 zeros and 6 ones here? So what I mean is, because we know there are 4 zeros, 6 ones in the original array. All right. So now we do not need to process the original array. Let's just pack 4 zeros here, 6 ones there, put them together, we get the array sorted. Can we do it in that way? Yeah. Yeah. Think about it. Yeah. But here, let me give you the answer. Yeah. The answer is no for typical real-world problems. Because our sorting problem, because eventually we want to solve the real-world problems. So our counting problem should match the real-world situation as much as we can. Okay? Yeah. Then it is useful. Otherwise, so you do something, but when you go to the real world, you get a completely different problem. So then you cannot use your current result. Yeah. So here, let's consider typical real world problems. Yeah. So what's that? So let me give you another concept, interesting concept. Satellite data concept. Satellite data. So in real world, we have the satellite data frequently. So we need to consider that situation. So let me explain that satellite data concept. Key value structure. Yeah. So in real, we frequently use the key value structure. You have key, you have value. So the key is used for search purpose. When you have a key, you use that key to do the search. Yeah. Then you get a value you want to use for your business. So the key value pair structure. So that's very common in the real world. Now we consider that structure. Here, in this example, suppose these elements have the key value structure. These values, they are keys. But each value for each element, other than the key, there is some satellite data associated with the key. Okay? Yeah. So the key you can use for search purpose. Yeah. But behind the key, there is a block of useful data. So we call it satellite data. Okay. Could be very useful, the data. So we don't want to throw away. Yeah. So we need to carry the satellite data all the time when you move the array elements. Yeah. All right. So when you arrange the elements, you have to use the original elements that carry the satellite data. So that's the background in the, many real world problems. You have that situation. Yeah. So now, so you can see under that situation, the answer here, you cannot simply pack several zeros, several ones, because you have to arrange the original elements containing the hidden satellite data. You have to make the arrangement coming from the original elements. Okay? Yeah. So for that reason, then we really need to develop some algorithm to rearrange the original elements. Not just, packing some numbers. Yeah. So that's not good. Okay? All right. So that means this way. Do not do this way. Okay? So, yeah. All right. So now let's, at this point, so we are doing some pre-analysis. Yeah. So before we solve it, we want to understand the problem as much as we can, because the understanding part is extremely important. Next, we need to solve the problem. We need to do the counting sort. All right, so